So let's talk about the concept of fields. A field of force exists in any region of space when an appropriately placed object placed at any point in the field experiences a force. We're familiar with two fields in our everyday lives. The first would be gravitational fields. The gravitational fields dictate that we stay here on the Earth, and if we drop something, we know it's going to fall straight down. Another example we could talk about is magnetic fields. We know if we have a compass, no matter where we are on the Earth, it's going to point towards magnetic south, which is our North Pole. So if I'm right here, and I've got a compass, I know it's going to point this way because this is the direction of the field lines towards magnetic south. So fields give us a way to predict the forces in action, these invisible forces. So when we talk about an electric field, what we're referring to is if we have an object that's very positive. Now this positive will produce a force. So if we take another positive piece right here, we know it's going to experience a force this way. Why is it going to do that? Due to the electric field. If we had a negatively charged object, we know the opposite's going to happen. We're going to have a force go this way. An example you might have seen in your other classes is when you get to gel electrophoresis. Now here are on the right side the four examples of the four different base pairs that make up DNA. We have thymine, guanine, cytosine, and adenine. They're four different structures. Because they have four different structures, they're going to have different charges. And this is going to be important for the concept of how gel electrophoresis works. So basically what happens here is you've got a negative end of a plate right here, and you have a positive end of a plate right here. Now what's going to happen is these molecules are overall negative. So you can think of this as being like a negative chest charge. Well, as a result of that, what do we have? Well, we have repulsion between back here and your particular piece of DNA, and you have attraction going towards the positive. And as a result, you're going to start to see movement occurring. And this is the result of the electric field being created in this direction. Now, if we think about it, these four different pieces of DNA have different charges. If it has a stronger negative charge, it'll feel a stronger force going in this direction. But if it has less negative charge, it's going to move less quickly. And that's why you see when you look here at all these different bands, how separation occurs. The separation occurs based on charge. So the more negative it is, the faster it'll travel through the electric field because it's experiencing that force. Now, whether you have a charge up here or you have a charge down here, they're all experiencing the same ratio of charges because they're feeling repulsion from the negative side of the plates and then attraction from the positive side of the plates. So when we look at the formula for electric field, which is the symbol of epsilon, it is equal to force of the electric field divided by the unit charge, which we represent as Q. Now as a reminder though, we defined force on the charge as equal to K Q1 Q2 over R squared. So therefore what we can do is we can take this and we can plug it into our equation. So if we do that, we end up with K Q1 Q2 over R squared Q. So these Q2 things are going to be the same. Both of these are going to represent the plates in these cases. So we're left with the equation of E is equal to K Q1 over R squared, with R being our particular particle of interest. And yet again, what we're thinking about in terms of distance is we're trying to figure out where we are on the plate. So we have our charge plates here. So the R is representing how far we are from one side or the other.